So good afternoon, everyone. Welcome to today's ECE Wireless Distinguished Seminar. My name is Rahman Dus Mohammadi. I'm a assistant research professor at ECE, and I'll be moderating today's event. So it's actually our great pleasure to have Professor Christoph Studer today. Christoph has received his PhD degree in 2009 from ETH Zurich. He has been also affiliated to RISE. He's not new to RISE. After his PhD, he spent 4 years at the postdoc position at both ETH Zurich and RISE. And after that, he moved to Cornell, where he was there till 2020 last year as a first assistant and then associate professor. Since June 2020, he has joined ETH Zurich as an associate professor there. So Professor Studer has won many awards, including medals for his MS and PhD, thesis at ETH, a US NSF Career Award, an equivalent of Career Award in Switzerland, as well as multiple Best Paper Award in international conferences as well. He also won Swisscom ICTNet Award twice. His research interests are at the intersection of communication theory, signal processing, machine learning, and ASIC design. So, Dr. Studer, it's great to have you today. Welcome back to RISE. Just before starting, I would like to actually give this logistical instructions to our attendees today. Please leave your questions during the talk in the Q&A section. At the end of the talk, we'll be asking those questions from Professor Studer, and we'll have a Q&A there. So with that, I would like to welcome you again, and please, the floor is yours.
Thanks a lot, Rahman, for the very nice introduction. Yes, I'm very happy to give this talk because, yeah, I'm not new to RISE. I spent quite a long time there and I miss it. Let me put this into full screen. And today I'm going to talk about how low resolution processing and analog to digital and digital to analog conversion can basically help massive MIMO systems to be more energy efficient and also achieve higher throughputs. Okay, so let me just dive right into it. So most of you already know that MIMO is used in almost all modern wireless standards. The idea is that you equip the transmitters and the receivers with multiple antennas, and you send data from multiple antennas at the same time in the same time and frequency band over a wireless channel, and then the receiver receives a mixture of the wireless signals and can sometimes undo the mixture, and then you can basically get higher throughput. You can also increase the coverage, you can increase the range without having actually more transmit power. And because of that, as I mentioned before, MIMO is used a lot in modern communication standards. But the problem is that like these small scale MIMO systems, so typically small scale means about 4 or 8 antennas on both ends, and also multi-user system where you have multiple users that transmit or receive, they are already reaching their limits in terms of the throughput that you can achieve. And of course, people are looking at like, what is next? What comes next? And over the last, I don't know, maybe 5-10 years, maybe more 5 years, people started looking at something which is known as massive multi-user MIMO. The idea is basically just to scale up the number of antennas at the receiver. So you have a base station where you have hundreds of antenna elements. We call the number of antennas B in this case. And because with so many antennas, what you can do is you can do very fine-grained beamforming, meaning you can direct your transmit and receive signals specifically to the users only. And you can basically increase the number of users that you can serve at the same time in the same frequency band. Also, if you have that many antennas, you can basically get a better array gain, you pick up more power, all these kind of advantages. And as I said, the idea is basically to have the opportunity to serve more users in the same time frequency resource using this technology. It's also believed that for systems that go beyond 5G, that we combine multi-user MIMO with also millimeter wave operation. So basically shifting from lower frequencies below 6 gigahertz to frequencies, say around 50 or even 100 gigahertz. And the reason is that these higher frequencies, bigger portions of the wireless spectrum is available, for communication. So we can again, basically, we have multiple users that we can communicate with, but we can also communicate with each user at a higher bandwidth. One issue at these higher frequencies is that we have more atmospheric absorption. So higher frequencies, we have like absorption in the air. And what you need to do, you actually need to do beamforming. So the combination of massive MIMO with millimeter wave is basically, or massive MIMO is basically a requirement at millimeter wave. Another thing that we are focusing on, so this is specifically for this talk, is what we call all digital base stations. So there's a lot of research on base stations that use hybrid receivers or hybrid transmitters. Basically what this means is that each antenna is not equipped with dedicated analog to digital converters, but we are focusing on systems where each antenna at the base station will have a pair of ADCs, so for the in-phase and quadrature signals, and also a pair of DACs for each antenna. We don't consider hybrid cases where we have analog phase shifters. And the reason why we're interested in all digital transmitters and receivers is because it allows us maximum flexibility for beam and null forming. So it's much easier to do certain tasks, for example, synchronization, channel estimation, finding beams, so basically tracking the users, pre-coding, equalization is all much easier. And also by having as early as possible in your RF radio frequency chain, analog to digital and digital to analog converters, you basically also minimize the amount of analog signal processing that you need. And people who know about analog signal processing, it's very difficult to actually build very good analog circuitry. So it's good to basically maximize the amount of digital processing in the receiver. Also because digital processing is much easier to test and migrate from one to another technology, semiconductor technology, which is very difficult, for example, for analog circuitry. So there will be some analog circuitry, but then as soon as possible, going into the digital domain and do equalization, channel estimation, pre-coding, everything in the digital domain. So if you look at this, basically all digital massive MIMO allows, with hundreds of antennas, would allow us to serve a large number of users. The problem is we end up with having that many antennas. We end up with having high dimensional data. So we have many antennas, we have many parallel streams, which we need to process. And on top of that, if we operate at millimeter wave, where we have, for example, 1 gigahertz of bandwidth, we would have to solve billions of tasks per second. So they're not just high dimensional, but you also have to solve many of these tasks at a very fast rate. On top of that, another issue with this technology is that the interconnect rate, so for example, the connection between the antennas and the digital processing, the baseband processing, could easily exceed the chip input-output data rates that exist nowadays. So it's very difficult to get the data into the chips. And on top of that, we have to process all this data. We have to do channel estimation, detection, pre-coding at these extreme throughputs. It's actually very difficult to do. And in particular, if you would just naively take small-scale MIMO systems and scale up these solutions to massive MIMO, it would result in excessively high power. System costs would be too much, and also the baseband data rates. So the interconnect data rates would be too high. So basically what this means is it's very nice to combine these technologies, but from a practical perspective, it's very difficult. And there's lots of roadblocks that need to be removed first. And here's maybe one of the motivations why the talk that gives kind of a motivation of what we're doing. So if you look at the power consumption in the radio frequency chains, so this is for the uplink, this is for the downlink, this is kind of like of a sub-6 gigahertz RF chain. And you can see here that the ADCs and the amplifier consume about half the power. And if you look here in the downlink, the power amplifier and the DACs consume almost 3/4 of the power consumption. So you can see that the ADCs and so the data converters and the power amplifiers or low noise amplifiers alone consume a large amount of power. So basically, by realizing that, this means maybe we should probably have methods that address these bottlenecks to reduce the power consumption, for example. And this is exactly what I'm going to do today. I'm going to show that massive MIMO can enable reliable communication with low resolution analog to digital and digital to analog converters. And we also show that after reducing the precision of the data converters, we can also reduce the resolution of baseband processing hardware. So the hardware that essentially processes the data can also operate with lower resolution. So everything we're going to talk about is about ADCs and DACs. And you will see this will be a recurring theme throughout. So basically, this is the main theme of this presentation. So maybe some of you may ask, so why is low resolution so good? Low resolution really directly implies lower power consumption. Since we have massive MIMO, we would have a large number of ADCs and DACs, But of course, if we can reduce the amount of bits per DAC, we can reduce the power consumption. And what is important is that the power of ADCs and DACs scales exponentially with the number of bits. So if you can reduce 1 bit, we can basically halve the power. On top of that, if we have data converters with low resolution, we can also reduce hardware complexity. And kind of the intuition behind this is that the remaining radio frequency circuitry only needs to operate slightly above the quantization noise floor of these ADCs and DACs. So you don't have to have very good RF chains anymore. They just need to be good enough or slightly better than the RF circuitry. Or than the ADCs. And also with the digital baseband processing, it's the same reason basically. You just need to be slightly better than what the ADCs provide. And we will basically exploit these two things, as you will see in the following. And on top of that, what I mentioned, if you also reduce the resolution, it will also reduce the data rates. For example, if you have a 256 antenna base station with 10-bit ADCs, which is potentially what a conventional approach would be, so conventional base stations may need or may use 10 bits or even more. If we operate them at 200 megasamples per second, this would already be 1 terabit of data, which is very difficult to transport, very difficult to get into chips, very difficult to process. So by reducing the number of bits, we can also reduce these interconnect data rates. So you can see there's many reasons for basically doing this. And what I'm going to show is that we can use low resolution in the ADCs for the uplink, and I'll explain what the uplink is later. I will show also how we can use low resolution in the DACs for the downlink, and then also how we can use low resolution when doing the baseband processing for massive MIMO. So this is basically the 3 parts I'm going to talk about, and how low resolution will help to reduce power, but also helps to achieve very high bandwidth or very high throughput. Okay, so let's start with the uplink first. For those who do not know what the uplink is when the user or the mobiles communicate to the base station. And we're going to look very briefly at a system that looks like this. We have a bunch of transmitters, and think about these being cell phones transmitting over a channel. And then we have a base station with B antennas, which is this massive MIMO base stations with a large number of antennas. And if we have here ADCs, so we have here ADCs for the in-phase and the quadrature, and imagine we have 1-bit ADCs. So 1-bit ADC basically takes an analog signal and converts it into, say, a +1 and a -1. The output that we get here at one antenna correspond to these 4 points. So we basically have 4 combinations of outputs that we will get here. And then channel estimation, data detection, all following processing will build on these 4 points that we get. If you increase the resolution of the ADCs, for example, to 3 bits, then we have for in-phase and quadrature, we have 8 levels each, and you basically have these levels that we have to use to process. So you can see this is the resolution that we get here at the output of the ADCs. So what I'm going to do, just to show a little bit of math as well, is we're going to look at a very simple system model, which also can be generalized, and I will talk a little bit about that. But basically what we have a received vector. This vector is basically what comes out here at the ADCs. And each entry of this vector corresponds to, for example, this finite alphabet here, this quantization alphabet. This Q function here is the quantizer, so basically does the quantization. And then we have a continuous model where H is the channel basically representing the individual transmit path and receive path between antennas here. We have the transmit symbols. This is what has been transmitted at each of these users. And then we also consider thermal noise as Gaussian model in this case. So we have a conventional model that goes through a quantizer, and we observe the quantized output in this case. So one of the key things is how can we deal with quantization errors? And maybe some of you took a signal processing class. Rice is famous for that. Imagine you have an input that is, for example, Gaussian, and we have a quantizer, where you can see here, this is this function Q, and we have a scalar output Z. How do we model these quantizers? And the simplest model would be we just apply the quantizer to this input, and we say the output is basically just the same as the input plus some quantization noise, or quantization error in this case. The issue with this model here is that the quantization error depends on the input Y. And if you want to do an exact analysis of a system with these, it's actually very difficult because of this dependence between these two quantities. So it's not as easy to do. We can also do the most complicated version. We just model this transfer function as a statistical, as a probability, as a conditional probability. So we say, what is the output given the input? And this has a known form. It can be written down, but actually turns out that theoretical analysis using this exact expression is very difficult as well. So it's very difficult to get closed form expressions or any insight using this. What we use a lot in this presentation, what has been used fairly often in the Mimo community recently is the following model. And it is known as a result from Busgang, so it's a very old result from the 1950s. And it's actually very similar to the first model. So you can see here, the first model, the output of the quantizer is basically the input of the quantizer plus some quantization error. But there is this small modification. So we multiply the output with a scaling factor. And if this scaling factor is chosen properly, you can actually make the quantization error uncorrelated with the input. And if you think about it, uncorrelatedness is some kind of a first order independence. And it turns out that now you can do very easily, you can do a theoretical analysis. It's easy to get SINR expressions. It's very easy to get lower bounds on mutual information using this very simple model. And this is one of these things that is very well known for those who know. The people working in analog circuit design have used that like for decades, but only recently has found use in, say, communication theory. But it's a very interesting tool because it allows very simple expressions and very accurate analysis, as I will show in a few slides. So let me show this, how you can use that. So for example, we had the system model that we have before, and we can now use this Busgang theorem. And basically what happens is in this case, so previously I was showing a scalar model, but you can also do a vector version of it. It turns out that this scalar quantity now turns into a matrix that we pre-multiply, and we have this error here. And this error here turns out to be statistically or uncorrelated to the input here of the quantizer. And if we have that, we can, for example, very easily write down a linear channel estimation because now the model is linear. So this is a matrix times matrices here and an error. So we can write down linear channel estimators. I'm not going to detail this expression, but they're actually very simple. And you can see this Busgang gain shows up. And this Busgang gain depends on how high the resolution and what type of ADC you have in this case. And then if you have a channel estimate, we can easily write down for example, equalizer or like a detector. In this case, we would just take the estimate. We would invert the estimate, multiply it to the received output, and we can actually analyze the performance in closed form using these kind of techniques. And you may ask yourself, oh yeah, we basically linearized something that is very highly nonlinear. So why would this even be a good idea? And it's interesting that it allows very accurate analysis, and then second, also very simple methods. The algorithms you've already seen, but now let's see how accurate the analysis is. So here we have a quantized uplink system. We have 200 antennas, we have 10 users. We consider some of the pilots, a few pilots. We have the SNR versus the uncoded bit error rate. And we have two curves. Basically, we have a curve here. The curve is the theoretical analysis that comes from these Busgang theorem expressions. And the markers correspond to simulation results. And you can see they match extremely well in this case. This is if we have one bit at the receiver, and you can see we get a fairly high error floor, which is probably not enough in a real system. But you can see that if we add, say, for example, we have 2-bit ADCs now, we get significant improvements. And you can still see the analysis is extremely accurate. If you go to 3-bit, we get an additional improvement. And you can also see that the 3-bit is very close to the infinite resolution case here. So if you had infinite resolution ADCs, with 3 bits, we can get very close. So basically, this already shows that, yeah, maybe 3 bits is good enough for practical receivers. And you've also seen on the previous slide that very simple methods would allow to achieve this performance. So very simple linear methods allow.
Hey, Christoph, quick question. In this analysis, only the quantizer is the only source of error, quantization, right? The ADC is the only source of quantization.
Yes, so just
computations,
the
computations are all full resolution.
In this, computations are infinite. You are like floating point resolution or infinite resolution.
Yeah. Okay. Yeah. All right. Thanks.
Okay. Yeah, and the key question here is also that we got a lot of like, okay, this is for a very simple narrowband system. Can you do this also for wideband system, for example, using OFDM? I'm going over this very quickly because there's a lot of details and it's not that important. But basically what we now do is we have some OFDM pre-processing at the transmitters, and we have OFDM demodulations at the receiver. And of course, the ADC is operating in the time domain in this case. What you can do is you can write down the optimal channel estimation and data detection problems. You can write this down as a large, surprisingly convex problem. Especially, for example, channel estimation can be written as a convex problem. And this is something to do when modeling these ADCs using a statistical model. The problem is you cannot solve these problems efficiently or fast or at the rates that you would need for massive MIMO systems. So there's no way you can do it, but you can do it in a simulation to see how well this would do. An alternative approach is just to say, let's ignore the ADC in a similar way that we did for Busgang's decomposition and see how well can we do with that. And I'm going to show a slightly different view to show that in principle, you don't need to solve these complicated convex problems. You can basically just pretend as the quantizer would not be there, and you can actually get very good performance. And the way we do is we plot here on the x-axis the minimum signal-to-noise ratio that is required to achieve 1% packet error rate. So this includes coding now. And here we have how many bits we use in the ADC. So this is bits per ADC. And this is a relatively small massive MIMO system with only 32 antennas, 8 users. And you can see here, if you have 2 bits, the performance is pretty bad of the exact model, and you can see the approximate model is even worse. So you need, basically, you need more bits to achieve the same performance with this. But then if you increase the number of bits, we can actually approach the infinite precision curve. Now, if you go to more massive MIMO, so you basically add receive antennas. So here, 64, now we have 128. You can see that, again, 3-4 bits, and you can get very close to infinite resolution. And you can also see what is interesting here is that the exact model and the approximate model perform basically the same. This means, like, if you have 3 bits, we can just pretend as if the quantizer is not there and say use 3 and 4 bits, and we can get very close to infinite resolution in this case. So this is actually an important insight, meaning even for OFDM, we don't need to do special, we don't need to be actually very much worried in doing so. We can just pretend the quantizer is not there. If you have enough bits, we can do very well. If we have smaller systems, so we have fewer receive antennas, or if we have very low resolution ADCs, then it actually helps. So if you go back here again, there is the gap is actually significant between the approximate and the exact model. But what is interesting also, like even if we have to use one of these complicated convex solvers, so I mentioned they're too complex, we've actually tried implementing this. So this is a little bit for the hardware people. We've tried to implement a receiver for 1-bit system. This hardware, I'm not going into too many details, but it's basically solving this convex problem in an iterative fashion. And we've implemented it on a fairly powerful Xilinx Vertex 7 FPGA. And what is interesting, we get a performance that is comparable to state-of-the-art receivers that don't have this quantization issue. So most of the receivers nowadays have been designed for high-resolution ADCs, but if we design one specifically for that, solving this convex problem, we can basically get a similar throughput per lookup table or throughput per complexity result as baseline. What we don't achieve with this implementation is a high throughput. You can see here the throughput is only in the megabits, but there are ways of scaling up the megabits, but we have not done this in this case. Basically, this will just consume way more area. Right now, the area is less than a few percent of the whole FPGA, but there's ways of like scaling up area and then achieving higher throughput. But the efficiency measured in throughput per lookup table is really comparable to existing methods. So this really shows that yes, we can deal with the uplink absolutely no problem if you reduce the ADC resolution. So basically, yes, I was just saying we solved more or less the uplink. So now let's look at the downlink, where the base station is sending data to the users. And you will see that downlink is slightly more complicated, also conceptually a little bit more involved.
Christoph, one quick question before you move forward. Yeah. In the previous results you've shown, is there a relationship between the size of the modulation and the quantization, or any order modulation you can actually work with it?
So here it depends a little bit on how strong you perform coding, but in principle, you can use higher order modulation. So not just QPSK, even with 1 bit. Even though you think 1 bit is losing kind of like the gain, but if you have multiple observations over the antennas, you can still do, say, 16 QAM. The question, of course, is what kind of an SNR are you okay with operating with? But in principle, yes, you can process higher order modulation.
I see. Okay.
But like exactly like which modulation scheme with how many bits and how many antennas, this can be analyzed, but I can't give you just like a number right now. This is not.
Got it. Okay. Yeah, but I guess there is an SNR loss to 1 bit, which may be larger with higher modulation. Is that a fair intuition, or?
Yeah, that's actually, so there's definitely like there's a kind of like an optimal choice depending on what point you want to pick. Yeah.
Okay. Okay. Thank you.
Okay. So let's look at the downlink, and I said it's conceptually a little bit different. So we have data that we want to send now to independent users. So basically what we do is we take the data and we have to pass it to something which is a precoder. And think about the precoder is kind of like transforming the input data. So when the data goes through the channel, it will be the same again. So kind of like pre-inverting what the channel is going to do in this case. And we consider that after the precoder, we have digital to analog converters that then get mixed to the carrier frequency through power amplifier and transmitted to the users. Let's for simplicity look at the frequency flat system model, and we can already see we don't see the quantizer in this system, and I will explain why. So basically what we have is we have this vector y here, which each entry of the vector corresponds what each of these users receive. H again models the channel, in this case models the downlink channel. And now what we have is we model this x here, and x is not what we send here at the input, x is what's coming out of the DAX. So our vector x is, each entry of the vector x is from a discrete set, which is basically the modulation or the finite alphabet from the ADC, from the DAX, sorry. And this vector x also needs to adhere to a power constraint, so we cannot blast with infinite power, so there's a power constraint on this vector here. And now what we need to do is basically this vector x is formed based on knowledge of the downlink channel and based on what we actually want to transmit to the individual users. So this vector x is a function of the channel and what we want to send. And then what we also have, we assume that, of course, we have thermal noise at the receiver here. So just think about this vector x is what's coming out of the DAX, and we have some function of mapping the data that we want to send to these users. And the idea, what the idea of this pre-coding in this case is we want to minimize the mean squared error at the receiver. So we have what the receiver should see and what the receiver actually sees. And in this case, this S hat is basically created when transmitting X through the channel. So we send this vector X to the channel, and then the receiver can also do some little equalization at the receive side. And then basically we want to minimize this mean squared error at the receive side. It doesn't really matter about the details, but basically you get this expression of what you want the users to see and what you're actually transmitting through the channel, and then scaled up using this beta. And there's some correction term which comes from the thermal noise that you have at the receive side. So we want to find this vector X that minimizes the receive side or at the user the mean squared error. And you can write down now this quantized pre-coding problem. You can find what vector X do I need to send if it goes through the channel and gets equalized is as close as possible to what the user should see. And of course, subject to a power constraint. And interestingly, this optimization problem is not just over the vector X, it's also with a scaling factor. So we can play around what the user scaling factor will be. And unfortunately, this problem is an NP-hard problem, and it's NP-hard because the entries of each vector are discrete. So this is basically a discrete optimization problem. And it's a very nasty problem that if we, in a sense that if we have, say, 256 base station antennas and we have 1-bit DAX, if we would need to use an exhaustive search, for example, for this, we would have to evaluate the objective function 10 to the 154 times, which is impossible. So this clearly shows we will never be able to solve this problem exactly. We need to find efficient ways that are approximate. So we need to find much simpler methods than solving this optimal. And there's a very simple approach. The simple approach is just we do linear pre-coding. Linear pre-coding basically takes what we want to send to the users. We multiply it with the pre-coding matrix, and then this is our vector. And what we do here is we quantize the output of this linear pre-coder. So we make sure that our vector X is then really, the entries of the vector X are really chosen from the quantization alphabet. And the interesting thing, this very simple algorithm, this linear quantized pre-coders where the symbols go in, we multiply with the pre-coding matrix, we quantize, again, can be analyzed via Boostung's decomposition. So using the trick I was showing before. And I'm going to keep this very short. You can basically see a very similar trend. So this is now downlink performance. And you can see here, again, analytical expressions are the solid lines and the markers are simulated. You can see the analysis matches very well. And again, about 3 bits, and you're as close as you can get to the encoded bit rate of infinite resolution, DAX in this case. The question, of course, is, but if we go here to lower resolution, say we go to 1, 2, or 3 bit, is this linear quantized precoder actually good? Or is it like, how much better is solving this NP-hard problem that I was showing before? And this result here illustrates it. So on the left side, we see the received constellation when we use 10-bit DAX. And this is the constellation that we would see at the receive side. This is at very high SNR. So think about it, there's no receive noise. Then you can just see the effect of the quantizer at the transmitter. If we use 1-bit DAX and we use a zero forcing receiver, you can see, or a zero forcing precoder, sorry, you will see here that the receive constellation is completely distorted. That will be very difficult to get reliable transmission. Now, if you would solve this NP-hard problem, you can see that you basically get something that is very close to the infinite resolution, even with 1 bit here. The trick here is we chose a very small system where we can actually do an exhaustive search. So in this case, we have only 8 base station antennas. So the complexity of doing an exhaustive search was kind of possible, at least in MATLAB. But you can see there's a significant difference in doing these simple methods or solving this optimal optimization, this NP-hard optimization problem. And of course, if you see this, then the key question is, can we get something that is low complexity but gets us close to the performance of solving the optimal problem? And it turns out that you can do that. And we call these kind of like nonlinear precoding methods. Basically, what we really try to do is we try to approximate this non-convex and this NP-hard optimization problem. You can see again, it has a vector in there that is discrete. We have some scaling factor. It's actually a very nasty problem. It's similar to a closest vector problem, but not really. But what you can do is, if you're a little bit clever, you can relax it in 2 ways. One is we can use something which is known as semi-definite relaxation, which is a very well-known problem, for example, of relaxing problems which is binary valued variables. So for example, 0, 1, or +1 and -1 variables. Or we have also designed an algorithm which we call Biconvex 1-bit precoding, or C1PO, which is basically solving this using a trick to formulate this as a biconvex problem, which you can then solve using alternating minimization. And I'm not going into too many details how these methods look like, but I'm just going to show you how well they work. So this is for a 1-bit system. So the transmitter has 1-bit DACs. The blue curve or bluish curve here is with 1-bit zero forcing. This is again this simple methods where we just do linear precoding and then we quantize. And you can see that the 2 methods we developed, so semi-definite relaxation and C1PO, basically get a performance that is about 3 dB away from infinite precision. And this is only for 1 bit. So with 1 bit, you can go very, very close in this to this one here. So you can see nonlinear precoders can do significantly better as these linear or quasi-linear methods that we were showing before. But of course, the question is, can you actually build them? And it turns out that you can. So we have implemented in our group C1PO. So this is the Biconvex method. This is a chip that is in 28 nanometer CMOS. It contains other things too, but here on the bottom, you can't really see it. But behind the top layer metal mask is actually the C1PO implementation that achieves actually a fairly respectable throughput for it being so small. And it's the first 1-bit precoder that is nonlinear that gets us very close to infinite resolution performance. So just this basically just proves that it can be done in practice. So we can do nonlinear precoding. We don't have to do these suboptimal methods. And this is particularly useful for systems where we really want to reduce the resolution to say 1 or 2 or 3 bits. If you go higher, then we can use simple methods in this case. So this was just basically again showing now, yes, so the downlink can be done as well. By reducing the precision, we can either have 4 bits and then we can just pretend as if the DAC was not there, or we can use sophisticated algorithms that can be implemented, and then we can also use 1, 2, or 3 bits in this case. And now what I'm also going to show is kind of like the next step is we can now also reduce the resolution of the signal processing itself. So not just reducing the ADC and DAC performance, but also the signal processing itself. And to show this can also be done for the downlink, but I'm only going to show the uplink in this case. We look again at the very simple model. We have our users that transmit data, go over a mmWave wireless channel, and then we receive it at the massive Mimo base station. And again, we have our model consists of a received vector. Each of these received inputs correspond to what we receive. In this case, H is the channel matrix, models these transmission paths between transmitters and receivers, transmit antennas and receive antennas. S is the transmit vector. This is what the constellation points we try to send. And then N is the noise that we try, the noise that we get here at the receiver. And basically the key point of the receiver, or one of the key tasks of the receiver, is to recover the transmitted data vector S, given knowledge of the received vector and also knowledge of the channel matrix in this case. And typical ways of doing this is using linear methods, but the goal of these methods is as follows. So what you want to do is you want to get rid of interference. So if you maybe look at this again, if all the users send at the same time, what you will receive is a mixture of all the data. And what you want to do is you want to basically remove this inter-user equipment interference. And also what it does, it takes the b-dimensional data, so all the data that you measure at the base station, and maps it onto U layers. So basically it's also reducing the dimension. And an interesting thing is this task has to be done at the ADC rate. So in this case, for a narrowband system, you have to solve this equalization problem at the ADC sampling rate. And what people typically do, for especially at these millimeter wave applications where you have these very large bandwidths, people just focus on linear methods. So basically what this means is you take your received vector and you multiply it with a matrix. And you can look at this in the following way. We have here the received data, and we have this array which basically implements a matrix vector multiplication. And the output here of this matrix vector multiplication would be an estimate of the transmitted stream. But it turns out that if you just take what people have done so far, so if you just take a naive way of doing this equalization for the 256 base station array, so an array with 256 antennas, if you would implement such an equalizer, even a linear equalizer, in order to support 1 gigahertz, it would be actually extremely large. It would be 27 millimeters squared. That's really big. And also the power consumption of this, only of this simple task, would already be respectable. So you would only this simple task alone would already consume more than 20 watts. So you have to be a little bit more clever to do this, to actually support 1 gigahertz of bandwidth. And it's interesting what you can do. So what I was showing before, we were focusing on like reducing the precision, but it turns out that you can not just reduce the precision of the ADCs, you can also reduce the precision of the entries of the matrix. And the insight is as follows. If you have a multiplication between two numbers, the area that you need to build that does not just depend on one operand, it also depends on the resolution of the other operand. And the area scales basically in the product, roughly in the product of the bits of both operands. And also the delay, so basically how long does a multiplication in hardware need, scales with the longer of the two resolutions. So if you pick the one of the two resolutions, the larger of the resolutions will determine your delay, or how fast can you do these multiplications. And the power consumption will be roughly proportional to the area. So you can see that if you just reduce the ADC resolution, but you keep the entries of this matrix W here, you would keep high resolution, you would not gain as much. But clearly what you would like to do is you would like to also reduce the resolution of the equalization matrix. And of course, a very simple way is you compute this equalization matrix. So in this case, this would be a Wiener filter or a MMSC matrix. You would compute it with high resolution, and then you would just quantize in order to make these multiplications cheaper. And you would quantize the rows of this so that the rows are binary valued with some optimal scaling factor. I will explain in a second why this is a good idea. And then the interesting thing is if we quantize this to just say plus minus ones, then multiplication would turn into basically subtracting and adding. So you don't need a multiplier anymore. And adders are significantly less complex than multipliers, so you will be able to do it significantly faster, and you will also do it at much lower power and lower area. But what I will show you now is like not as easy. You cannot just calculate these weights at high resolution and then pass it, quantize it and use it. So this is now what you would do, what you would get if you would run your receiver at infinite resolution. But if you quantize this equalization matrix to 1 bit, you see you get a significant performance loss here. So this is just computing the high resolution equalizer and then quantizing the weights. And you can see here the loss is like almost 8 or 6 to 8 dB in this case, depends on where you look. Of course, probably it was not the way, it was not an optimal way how we did it. Like calculating at high resolution and then quantizing may not be the optimal way of computing these equalization weights. And what we can do is we can actually do this in a more principled way. So what we want to do is our ultimate goal is to achieve a low power, low area equalizer. So we can design our equalizer this way. And what we do is instead of using just a low resolution matrix, we split our equalization matrix into 2 parts. First, a matrix part, which contains, for example, plus minus ones in the real and imaginary part, followed by row-wise scaling or entry-wise scaling here using a vector B star. So this is a two-stage matrix. First part of the matrix is high resolution. The second part of the matrix, is low resolution. And the second part of the matrix is just row-wise scaling with a diagonal matrix, which can be high resolution. And this also would lead to, basically, this is a 2-stage equalizer. First, a low resolution matrix vector multiplication, and then followed by a high resolution scaling. And the reason why this is interesting, if we apply this matrix to our received vectors, we would have to compute these low resolution in the product. So the XU Hermitian is one row of this X Hermitian matrix. We would do a low resolution in a product. And since it's low resolution, it would only need adds and subtracts. And then after doing this in a product, we would multiply with a high resolution scaling factor. And that's kind of the structure of the equalizer we want. And since we have only here a inner product with, say, a plus minus one matrix, this inner product can just be done by a series of subtract and adds. We don't need any multipliers. We then only need per user one multiply. And that's why this way of designing these finite alphabet matrices allows lower area, faster throughput hardware in this case. The problem is, like, how do we compute these two matrices? How do we choose the entries in X, in this matrix X, and how do we choose the optimal scaling factors? And what we can do is we can write down a finite alphabet MMSE equalizer. So we can write down what is the optimal choice, the choice that minimizes the mean squared error. We can write that down. And this is an optimization problem in this vector beta and in this matrix X in this case here. And you can already imagine that this problem here can be reformulated in multiple ways. And then it's also interesting, it can be split into two parts. You can first compute the row by solving this problem. And as soon as you know how one row has to look like, you can find the optimal scaling factor. So solving this problem here at the bottom accomplishes exactly the same thing as solving this one. So you can solve it in two stages. But unfortunately here, the first part, like finding these plus minus one vectors, is, as you can already expect, is again yet another NP hard problem. And again, because it's a fraction of a quadratic term. It's a fraction of two quadratic terms actually, and we have the vector is discrete, so it actually turns out again to be in general NP hard. And again, if you have 256 antennas, solving it is basically impossible using an exhaustive search. But we know what the optimal thing would be, but there's no way we can do that. And of course, you probably would ask, like, what does it even do? Does it even help? Let me maybe show the first one here. If you use infinite precision linear mean squared error, this would be the receive constellation. This is now at 15 dB SNR. If you just quantize the equalizer matrix, this was the simple method I was showing before. We get a complete mess. You can see this basically there's no way we can get reliable transmission. But if we solve this finite alphabet MMSE equalization problem, we can get something that is very close to infinite resolution, even though we have one bit weight in the matrix itself. And you can see here, if you look at the error vector magnitude, it's on the same, it's comparable to the infinite resolution, and it's about half of that of the simple method that I proposed at the beginning. But of course, like, it would be good to solve it, but we do not know how to solve it. Again, to create these plots here, we chose a very small system where we can do an exhaustive search. But of course, in massive MIMO, we may have more than 100 antennas. So what we need to do is we need to design faster methods. And there's actually a lot of interesting algorithmic tricks in there. But basically, you can use something which is known as a Dinklebot method for this fractional program that I was showing before. You can take this fraction and you can split the fraction into two parts using this gamma parameter, which is kind of like the value of this optimization problem at the optimal solution. So imagine you know the optimal value, you can kind of like reformulate it in this way. And now what you can do is you can relax the discrete nature of the transmit vector, so that before it was, say, plus minus one, but you can take a convex relaxation. You could say let's allow everything in between -1 and 1, and then you can solve it using forward-backward splitting, which is basically a gradient step and then a projection onto this constraint, a gradient step projection. So the algorithm is very simple. It's a affine transform and then followed by a nonlinear step in this case, and you have to just repeat this a bunch of times, and then you get hopefully converge to a good solution. Again, I'm not going into too many details, but I want to show one more thing that you can do with this. And this is a trick known as deep unfolding. I think every talk nowadays needs to have some machine learning in here. And what you can do is, what I was showing here before, we have an affine transform in each algorithm iteration followed by a nonlinearity. You can take this algorithm, you can unfold it. You can say, let's do 3 iterations. And then it turns out that this algorithm looks like a deep neural network where you have an affine transform, which consists of multiplications and additions. And then you have this proximal operator, which is an element-wise nonlinearity. Then you have again an affine transform, element-wise nonlinearity, affine transform, element-wise nonlinearity. And why do we do that? Now, the cool thing is we have these algorithm parameters like step size and the optimal objective function. What you can do now is you can use tools from neural networks. You can use whatever TensorFlow or PyTorch to offline find the best step sizes and lambda parameters. So you can throw this into a simulator that generates a huge amount of data and a huge amount of channels, and then you can optimally tune the parameters automatically. In this case, you don't have to do manual tuning of your parameters. You can find optimal solutions using this. And the interesting thing is, compared to a manual solution, like imagine we pick these parameters manually. That's what we used to do. But if we use this deep unfolding, it actually turns out that we can reduce the number of iterations by about 2x for exactly the same performance. So we can get about to 5 to 10 algorithm iterations, and we get reasonable performance using this. And just that you remember that it's known as deep unfolding. This can be done with many other algorithms as well. So this can be done, has been done in signal processing. It's been done for convex, non-convex problems, and also can be done here in wireless receivers. So let's look very quickly about the performance of that. I think I'm running out of time. Again, if we use 1 bit and we don't really take special care about how to design these equalization matrices, you can see here in this case, the performance is pretty bad. But if we solve our FAME problem, so we use here the problem, we get significant improvements. This is for 1 bit. If you go to 2 bits, we get even closer. And if you go to 3 bits, we are very close. And you can also see for 3 bits, it's good enough to just compute with infinite resolution the equalization matrix and then quantize the entries. So this FAME, what I was showing before, is very useful for if you want to do really low resolution baseband processing. But if you can afford, say, 3-bit processing, then it's good enough to just normally compute your equalization matrix and then just quantize the entries. And maybe not the last thing is something that is very interesting. If you now reduce the resolution in the baseband processing, you can start using kind of like emerging hardware tricks. And if you build normal hardware, what you typically have, you have processing elements and you have memory, and your data goes in through the processing elements, and the processing elements have to like gather the memory contents. You multiply them, for example, you output them. What you can do instead is you can basically fuse memory and processing elements, and then just pass the data through your memory and processing. Some people call this in-memory processing, but in our case, because the data is really going through the memory, we call it through memory processing. So basically, think about it, the memory and the processing sits at a fixed location, and the data is just going through that block. And we have developed such an accelerator. We have developed one thing we call 2PAC, or PPAC in this case. It's called parallel processing and associative CAM, and it's really useful to accelerate matrix vector product like task in this structure here. And it doesn't use any emerging technologies. It's standard cell based, but it actually gives significant improvements in practice. So if you have a 10-bit architecture, for example, for this equalization, and we go to 3-bit, we can already get an improvement. But then using this PPAC accelerator, we can further reduce the area a little bit. In terms of area, it's not as impressive, but in terms of power, you can see here, if we go from a traditional architecture to so an architecture that uses our finite alphabet processing, we can gain something. But then if we use our PPAC accelerator, you can see that this is almost like half the power again. So we can reduce the power consumption by an additional factor of 2 for 3 bits here. If you would do this for 1 bit, which we can also do, then we get about 9x area and power reduction in this case. So reducing the number of bits does not just like lead to simpler hardware, but we can also now use these new emerging hardware technologies like processing in memory to even further reduce the area and the throughput of these architectures. Of course, the throughput is going to be extremely high for these architectures because they're completely isomorphic. So you will basically solve one of these problems per clock cycle. The throughput that you achieve are very, very high. And everything you've seen in this talk, so we've looked at the uplink quantized and the downlink quantized and the baseband processing. We have implemented a chip recently. So this is a brand new result. We have the chip right now on our tester here at ETH. This is the first all digitally received beamformer. So this contains ADCs and contains finite alphabet baseband processing, contains channel estimation, contains beam space processing, all sorts of things. Yeah, so stay tuned. So basically, this just shows that we can actually combine it and build these receivers in this case. So this is a very new thing. We hope to be able to publish that like at ETH or ICCC, which is past, but maybe TVLSI, some of these conferences. So let me conclude. So just to summarize what we have done, So if you would just naively take small-scale MIMO systems and we would scale them up, we would eventually end up with excessive system cost and power consumption, so it would not be a good idea. But what we can do is we can exploit the fact that we have now massive MIMO, we have this high redundancy of antennas to reduce the resolution of the data converters and also reduce the resolution of baseband processing itself. Reducing the data converters has been done over the past maybe six years, but reducing baseband processing is like something that is very new, like maybe the last year or so. Another thing that I would like to, as a take-home message, is that even if you have a quantizer in your system, it doesn't mean that you cannot analyze it. You can use Buscan's theorem, for example, to do these analysis, and you've seen before how accurate they are. You can get very simple SINR expressions, and you can get lower bounds on the mutual information very easily. Another take-home message is that if you can afford 4 to 6 bits in your ADCs and DACs, you can basically just pretend as if you had infinite resolution and you're all fine. If you go to lower resolution, you need to use more sophisticated algorithms. And then also baseband processing, 1 to 3 bits is good enough to get very close to infinite resolution. So you don't need to have these high resolution multipliers in your hardware. You can really reduce that as well. And then also you can start looking at these emerging technologies like in-memory processing, what we call, in our case, through-memory processing is extremely beneficial if you have really low resolution processing, because you can now move the memory easily into your processing elements. And basically you can build kind of a memory that processes your data. And of course, everything we've shown so far can be implemented and also has been implemented in our group. So it's totally possible to do these things. With this, I would like to conclude my talk, of course, thanking all my collaborators, my student, Oscar Castaneda, who hopefully stays as a postdoc, so we can do some more stuff. And of course, the collaborators from Chalmers to Professor Giuseppe De Rusis was involved heavily in the low resolution analysis of low resolution uplink and downlink. We have also some parts of the work, the optimization part of the work was done in collaboration with Tom Goldstein, who also spent some time at Rice. And also we have some contacts worked with Ericsson, Sven Jakobsson. He was a student at Chalmers, but is now at Ericsson. A lot of the results also with him. As usual, we have to acknowledge our sponsors, but I think what is more important, if you need more information or if you have any questions, please visit our institute's website and then you can go from there. Thanks a lot for listening, and now I'm very happy to take tough questions.
Okay, thanks a lot, Christoph, for this fantastic talk. So I guess, yeah, we have, looks like some questions. Santiago.
Yes. Hi, Roman. Hi, Christoph. Thanks for the talk. This is Santiago Segarra. I have 2 quick ones. So the first one is, in 2 different points, you had kind of these quadratic problems on the discrete variable x, right? One in the downlink and then also in the band. And at some point, you used this C1PO, kind of a biconvex way of trying to solve this problem. And then in the baseband, you use projected gradient descent, right? So any reason why you use these 2 different approaches to attack these problems that seem to be similar?
So yes, so the problems are slightly different. You see here is basically a fractional program that we turn into something like that. Then I don't know where I have it. Let me see where I have it. I have it later. Yeah, you can then turn it into something like that, which is really, you can calculate the gradient of this. You can easily calculate the gradient of this expression and then projecting. In the other problem, I mean, I can go back. It's not as easy to do. You can also do it, but it doesn't work as well in this case. And also it turns out that, so the interesting thing is, and of course I've skipped more or less everything. Let me see if I can find the C1PO thing. I wonder where that was. C1PO was somewhere here. Let's see. Where is it? I don't have the method, the algorithm. Yeah, you can't really see it. But basically, it's the iteration that you have. I don't have the algorithm here. Yeah. Looks very similar as a projected gradient descent, but is essentially kind of like an alternating minimization procedure. But it looks very, very similar. Yeah.
That's great. So did you try and unfold this C1PO already, or is that in the pipeline, or?
Yeah, we have done it. Let's see where. I think somewhere we have done it. Yes. Let's see. So the interesting thing is what I didn't mention here is, yeah, somewhere there's a paper. See, I'm completely lost. Yeah, neural network optimized 1-bit pre-coding here in this case. We have done it. We have not implemented it because the implementation stays exactly the same. Yeah. Because the only thing that changes are the step size selections, which is already built in the hardware. So the only thing is, like, before that we tuned them by hand, but now we use neural networks to tune them for us. Yeah.
Right. Got it. And another quick one. So when you go for this frame, right? So that you had this diagonal matrix of beta star multiplying the x. Mm-hmm. So before you, yeah, exactly right. So before, in the previous slide, you had something like just using the quantization of minus beta to plus beta, right? That one there, which is, it is basically what you have in the basically frame, but with a scalar instead of a diagonal matrix. Is that right?
Yes. I mean, it can be exactly the same. If the entries in X are binary, it's the same.
Exactly. If it's 1 bit there or something, then it's the same thing, right?
Yeah, but here we quantize, like the way we get it is different, right? Here we just quantize the infinite resolution solution, right? But here we actually, in this method, when we then do it here, we actually find what are the optimal selection of plus and minus ones.
Right. I see. So there are these two changes, right? So one is having the user-specific beta. Yeah. And then the other change is having the X found in a different way. Right?
Yes, basically finding the optimal sequence. Yeah.
I got it. Is there any motivation to go like somewhere in between, like instead of having just the same beta for everyone or one beta per user, having kind of betas per blocks of users or something? Does that make sense at all?
Yeah, so it turns out it's very important to have it per user, because in these systems, different users can have a completely different gain because of the difference of the antenna. I mean, there's some power control, but they will have different receive power or transmit power. So it's very important to do it per user. So a common gain or sharing doesn't really help, and it also would not really simplify the problem. It would actually make the problem more difficult. If you have a common gain, I'm not sure, I've skipped that again. I'm skipping a lot of details. You can solve this problem per user. Right. If you have a common gain, you suddenly have to do the joint problem on the whole matrix, which is even worse to do.
Yeah. The problem, I guess, is worse. Maybe the system gets less area or whatever, but maybe the gain is really important.
You need multipliers anyway for each user, so whether they're variable or not doesn't really matter.
That doesn't matter. Okay, cool. That's great. Thank you, Christoph.
Okay, thanks, Santiago. And so next question from Joe. Joe, you want to go?
Sure. Okay. Yeah, I had two questions. Really enjoyed the talk, Christoph. Always very good work. In the beamforming that you're doing with the low resolution, I assume you're assuming uniformly distributed far field users. Do you see any issues that may come up if they're not uniform, if they're clustered in some way? Would that have any effect on the resolution choice?
Yeah, so this is a very good question. So when we simulate these results, we typically we basically place the users in a sector with a certain sector with a certain distance profile, so they're not uniform at the same distance. But what we do is we make sure that the minimum separation, angular separation, is larger than a certain value. And the reason we do that is because then otherwise the channel vectors or the channel coefficients will basically be collinear and you will not be able to separate them. And the motivation behind this, you can think about there being some scheduler that makes sure that if you have two users with a very similar direction, that you're not serving them at the same time. You need that, otherwise it's just not possible. Not even in the infinite resolution case, it would not be possible. Okay. Yeah. And I also agree that if you have a larger dynamic range between users, you need more bits. So one of the reasons why we always write 4 to 6, the 6 is really needed in cases where you can have an extreme range of near and far users. If you have very good power control, say plus minus 3 dB, then 4 dB, then 4-bit is good enough. But if you allow like very large range between powers, then you need more bits. Yeah.
Okay. So I mean, that was another question. In terms of the chip at the end, is that including the A to Ds, D to As, and also the low precision arithmetic, or is it a mix of all three features?
Okay, let me see. So
the final chip picture.
Yeah, it's a nice picture. I want to show that. Yeah, so it actually contains the ADCs, and they're programmable in resolution. So you can choose the resolution you want. Then it contains this p-pack array or 2-pack array, basically what I was showing, where you can choose also the resolution. So you can either do 1-bit, you can do 3-bit. So all the resolution is programmable. But it's not on there is the downlink. So this is just a receive chip, but the downlink chip will basically be very similar. Yeah.
Okay, so you could be able to adjust then the resolution on the fly for those different angular separation issues with different users?
Yes, you could do that. I mean, what we kind of had in mind is like if you have fewer users, say imagine you only have one user at a time, you do not need to have high resolution ADCs. But if you have more users at the same time, you need more. So you can play that trade-off in real time using this approach. And also we wanted to measure the actual trade-offs using that chip. Like what are the actual gains of having this these different resolutions? Because nobody has really done this based on hardware. That's kind of the motivation behind it. Yeah.
Okay, very good. Thank you.
Okay. Thank you, Joe. So yeah, I guess we're out of time. But yeah, so I think we can just leave it here. So thank you so much, Christoph, for the great talk, and we hope to have you sometime soon in the future, physically at Rice as well.
That would be awesome. Yeah.
Right. Yeah, and then we're looking forward to meetings, the meetings with you after this talk as well. So thanks also everyone else for attending this talk. I hope to see you next time. Thank you.